Right now, the air inside the room you are sitting in contains liquid water, not humidity, not vapor, actual H2O molecules, suspended and invisible, floating right in front of your face. I built a machine that pulls that water out of the air and turns it into something you can drink. It uses basic parts you can order online right now, and the total cost of the build is $30. Most people assume that extracting water from the air requires massive refrigeration systems or commercial-grade equipment worth thousands of dollars. Commercial units are expensive, but the reason a commercial unit costs $5,000 is due to materials, certifications, and profit margins. The physics behind the process costs exactly $30. Once you understand the underlying mechanism, you realize the barrier here is a simple knowledge gap between thinking this sounds impossible and seeing how obvious it actually is. The concept that makes this entire build possible is the dew point. You see this happen when you pull a cold glass of lemonade out of the fridge on a hot summer day. Within 60 seconds, the outside of the glass is wet. The air around that glass hits a surface cold enough that the water vapor has no choice but to convert back into liquid. The dew point is simply the temperature at which air can no longer hold water vapor as a gas. Our engineering challenge is figuring out how to create a constantly cold surface cheaply without using a compressor or chemical refrigerants. We solve this using the Peltier effect. When you run direct electrical current through a junction of two different semiconductors, like this TEC1-12706 module, one side gets hot and the other side gets controllably cold. When you apply 12 volts of direct current to this cracker-sized module, the cold side drops between 5 and 15 degrees Celsius. That is well below the dew point in most of the United States. We now have our artificial condensation surface. Step 1. Assembling the thermal core. Apply thermal paste to both faces of the Peltier module. It's sandwiched between a large hot side PC heatsink and a smaller cold side heatsink. Press them firmly together and clamp with strong binder clips for perfectly efficient heat transfer. Here is where most DIY atmospheric water generators fail. It isn't the electronics. The primary point of failure is thermal management. This thermal visualization shows exactly why. The Peltier module is essentially a heat pump. It moves heat from one side to the other. If that hot side heatsink cannot reject heat fast enough, the temperature differential collapses. The cold side warms up and condensation stops entirely. To maintain the temperature differential required for condensation, the hot side exhaust must be heavily oversized. Bigger is always better for this specific component. Next, we modify a standard styrofoam cooler. You need to cut two holes into opposite walls, one for air intake and one for exhaust. The cold heatsink sits inside the cooler. The hot exhaust fan stays outside. An intake fan pushes humid air across the cold block. A stainless steel plate attaches to the cold side, angled downward. Condensed water flows down the slope into a collection container. Every surface the water touches must be strictly food grade. You cannot use galvanized steel, as the zinc coating is toxic. You cannot use standard PVC adhesives because they off-gas into the water. Wiring is straightforward. Connect the positive and negative terminals of the Peltier module and both fans in parallel to a 12-volt 10-amp power supply, like a used laptop charger. Proper housing, controlled airflow, and safe gravity routing turn a simple demonstration of physics into an organized, functional water catchment system. Within an hour of powering the unit on, you will have measurable water in your container. But the raw water dripping off that stainless plate is not safe to drink yet. Ambient air contains dust, mold spores, pet dander, and airborne bacteria. In urban areas, it holds volatile organic compounds from vehicle exhaust. When you condense water vapor, everything suspended in that air condenses right along with it. This cross-section shows the required safety stack. First, water passes through a mechanical pre-filter, catching debris. Next, an activated curtain block removes chlorine and volatile chemicals. Finally, a UVC LED sterilization module destroys pathogen DNA, killing 99.9% of bacteria without adding chemicals. Building the physical machine is the easy part. Implementing the strict filtration stack is what separates a dangerous amateur science project from a legitimate, safe survival tool. Running continuously in a high-humidity environment like the Gulf Coast, you can expect a realistic output of roughly 300 to 700 milliliters per day. The machine draws about 120 watts continuously. Based on average US residential electricity rates, that costs roughly 46 cents a day to operate. This $30 active build is an excellent proof of concept and a legitimate emergency source, but it is not a total replacement for your household tap water. The Peltier method has a hard ceiling for output. If you want to scale up and produce gallons of water per day, you need a completely different mechanism, one that uses passive cooling and runs on zero electricity. Mastering this basic active build is the essential first step. Once you understand the physics here, you are ready to attempt the massive off-grid passive water generation systems we cover in the next video.